So for prefix sums, so again, prefix sums will help us solve any range sum query. So for example, if we have any range inside of this array, it will allow us to get that sum in constant time. And to do this, we will need the help of a prefix array, which will basically get the sum from the range 0 to I, right? So for example, let's say that we've already calculated this prefix array, and let's say, like for example, prefix of 5 would be the sum range from the beginning of the array, always from the beginning, to 5, right? And somehow we can manipulate this prefix array to help us solve the some sort of sum in the range over here, right? Because right now, this prefix only gives us the sum from the beginning of the array up to some point, but doesn't necessarily give us any range. So let's see how we can do this using some sort of illustration. So I've just written this array out on this notepad over here. Again, the things that we've already computed, we've already computed the prefix sums. So we've computed this sum over here, this sum ranging from here, right? Always starting from the beginning. Okay, then this as well. And I skipped these, but like we've computed those already. So let's actually say that those sums we store in this prefix array. So I'll just call it, actually just call it prefix, right? Or just call it P. Okay. So in this P over here, maybe align this a little bit better. Okay. Right, so the sum of 1 to itself is just 1. Sum of 1 and 2 would be 3. Right, oh my god. And then 3 plus 3 would be 6. Right? And then 9. And then 13. And then 14. Then 14. Cool. And again, this is all well and good, but like, how do we actually get the sum from, for example, this range, right? Because our prefix sum only, again, includes like the stuff from the beginning. This looks like a B. Why does this look like a B? Let me change this to 13. Okay. Yeah, so what we can actually notice is we can take this sum over here. Oh, I extended it too far. We can take this sum over here, and then to get this sum over the sum that we desire, we can just subtract this sum over here, right? Because we've calculated all the sums starting from the beginning. So you can just take the whole sum up to that rightmost index, and then subtract the sum before, and then that will give us the sum over here, right? We can verify that. So, the big sum that we have from this one to this one will be 14, right? 14, and then the sum over here will be 3. So our answer over here should be 11, right? Let's manually calculate that to see if that's correct, right? So it would be 6, 10, 11. Cool. And this works for like any sum, right? So any range, sorry. So let's say that our range was this, right? Or we would just calculate, use this prefix sum over here minus this prefix sum. And it kind of makes sense, right? Like this minus this would be equal to this. And also just if you add these two smaller ones, it would also equal the bigger one. So I guess that makes sort of sense intuitively. So to generalize this in like some sort of a formula, we would just say, let me move this down maybe. Okay. I'll put it in the middle. So let's say that actually, sure, that's fine. So let's say that the left was here, right? So the left bound was here, and then the right bound was here. Right? So this is all inclusive, right? So it's going from left to right inclusive. This is the range that we want to solve. The answer would just be, and I'm going to use this as a prefix array. The answer would just be P of R, right? P of R, which is this like huge interval over here, subtracted by this smaller interval, right? So this is left, it would always just be left minus 1. So minus P of L minus 1. Yeah, and then that would be our answer if we wanted to get the sum from L to R. Okay, one small thing that you might notice if is like, what if we actually want to start from 0, right? If we want to start from, sorry, the 0th index, if we want to get this range, let me move this up a little. If we want to get like this range, right, so L in this case would be here, and then R would be this, right? This would actually sort of crash like our formula over here, right? Because prefix of R is fine, but if we do L minus 1, this will actually go out of bounds. It would be a negative index. But that's actually fine, because what we can do is we can just take care of this case to see, okay, so if like we were starting from the 0th index, then our answer would just be P of R, right? Our answer would just be what our prefix sum originally calculated was, right? So yeah, that's just like some sort of small caveat that we'll also have to take care of. So let's actually try coding this out. Okay, so I already have the input array, and L and R is what we're going to be doing to see the sum query after we compute the prefix sums. Okay, so let me actually put this stuff on the bottom. So we can declare a prefix sum, and then how big is this going to be, right? This is going to be as big as the original array, right? The same amount of numbers. So to calculate, right, so like even before we start doing the subtraction stuff, we need to calculate the prefix array. Okay, so the prefix array will be, right, so the first number will start as just equal to the first value inside the array, right? So P of 0 is equal to A at 0. And then for the rest of these, right, we can do a loop. So you can say for int I is equal to 1, I is less than a dot length is plus. You can also do p dot length. They're the same lengths. Might actually make a bit more sense to use p because you're sort of looping through the p array. And then just see like, okay, so this 3, what we have to do is just use the previous index sum plus this current value, right? So this would just be p at I is equal to p at I minus 1 plus a at I. Okay. And like, right, you can kind of see how that works, right? So if I'm trying to calculate p of 2, right, this is at index 2, this will be equal to p of 1 plus plus a at I, right? So hopefully that makes sense. And then I guess like another thing is like, why do we like not just start at 0? Like, right? Like, why do we not just start at 0? The reason why we can't start at 0 is because this I minus 1 will go out of bounds, right? So we just take care of the 0th case first, right? That's all well and good, like not too hard. It's just the 0th element, and then for the rest of them, we can use I minus 1 now, because we would know that we won't go out of bounds. Okay. So after we calculate the prefix array, now we can do our sort of fancy subtractions. Because prefix sum sort of new, I think it might be helpful to just use a separate function to calculate it. So it's like just sort of clear like what we're doing. Now inside this function, there's just going to be one line of code, but I still think that it might help a little bit. So I just say this is a sum query. I'll just say sum q. Now take in an L and an R. And just to document this, we'll say that this returns the sum of some range from left to right, L to R inclusive. Okay, from indexes. Yeah. And then we'd also need to pass in the prefix array as well, right? Okay. So again, our formula is just P of R minus P of L minus 1. So just return P of R minus P of L minus 1. Okay. But again, we need to take care of that case where like L is 0, right? We don't want to go out of bounds with this L minus 1. So we can actually just put a statement over here and be like, okay, if L minus 1 is equal to 0, then we will return just P of R. And then we're also like sort of just assuming that L is less than or equal to R and are valid indexes in the array. Sometimes we're using 0 indexes over here. Sometimes the questions ask for like 1 indexing or whatever. I generally just derive the formula again, like depending on what we need. So the more important part is just to know like like how we came about deriving this prefix sum, because a lot of times with these algorithms, like don't really memorize them, but you can come up with them again. Okay. Cool. So if we wanted to get this query, then we would just do sysout LR, right? And then we'd also pass in P. Oh, sorry, we need to call the function LRP. Okay, so let's see if this is correct. So 1 to 3 would be 1, 2, 3, right? That is actually incorrect. Why? 3, 6, 9. Yeah, so we have 9 over here. Oh, okay. 1, 2, 3. So that will be, we're trying to get the sum from here, right? So it would be 9 minus 1, which should be 8. Oh, sorry, this should be less than 0. Okay. Yeah, okay. Cool. Okay. Yeah, and again, like, I don't have this memorized. Every time I sort of use prefix sums, I have to kind of derive it again. I guess it's sort of slow, but I think it should be fine. Cool, right? Because like this has to be less than 0 if we want it to be negative, right? Not if it's equal to 0, that's fine. But we don't want this part to be negative. Okay. Let's just do another sum query to make sure that this works, right? So if we started from 0, and then we go to index 2, this should give us 6, right? Okay, and there's 6. And then let's say we go from, I don't know, index 2 to 2. This should just be 3. Okay. Okay, cool. So let's like sort of just analyze the time complexity of this prefix sum, right? So if we have an array, right, this will already be O of n. You can kind of think about it. Because at least in Java, how it happens is to create an array, you need to allocate that much space to it. So you can just think about it as there's like n operations here. Okay, n operations. Or I'll just say this is, yeah, this is fine. And then to create a prefix array of that same length will also be around n operations as well. And then, right, because this is going to be the same length as this array. Oh, sorry, n is going to be, I'll just say n is the length of the array. Okay. Operations. And then this part, right, so this is just one operation. And then this part is, I guess, a bit more interesting. But it would only take still n operations, right? Okay. And then this single query is just going to be one operation. Operation per station. And then all of these, like, these variable declarations or this assignment is just going to be one operation as well. Okay. A lot of times, I'm just going to highlight it here, but like, I'm just going to like write it out here, but like you kind of can ignore these. What you care more about are like the bigger loops and stuff, and maybe sometimes array declarations, right? So if we sort of add all the operations up, right? So I have n, right? So there's 3n plus 1, 2, 3, right? There's a rough estimate how many operations we have. This would just be big O of n. Okay, so this is big O of n, which is fine. And even if we do the operations analysis from last time, 3 times n, let's say if n was like 10 to the 5, it would still be a lot less than 10 to the power of 8, right? And a lot of times, again, I'm just ignoring the smaller operations because, like, in the grand scheme of things, like 3 operations is nothing compared to like 10 to the 5 or 10 to the 8, right? So, yeah.